Today I'm going to talk about design and operation of hybrid power plants with Power2X using the HyDesign tool, as Jen mentioned. So I'm Megha Gupta. I'm a postdoc at the Department of Wind and Energy Systems at the Technical University of Denmark. And to begin with my presentation, firstly, I would like to give a brief background upon what is hybrid power plant and what kind of hybrid power plants are we modeling and are we studying at DTU Wind. The hybrid power plants we are focusing upon are the utility scale and co-located grid-connected power plants. Here, if I'll just go into the details of the configuration of hybrid power plants, then we have a wind power plant, solar power plant, and energy storage systems, which are all co-located behind the single point of grid connections, and we can accommodate more than one generation sources. And also on the top of that, electrolyzer, which is converting the power into hydrogen, can also be added at the same point, the same configurations, and we can produce multiple energy vectors like electricity and hydrogen, or maybe like ammonia, methane, methanol, etc. from such facility. And what is important to note here is that we are considering a common hybrid power plant controller for this whole setup, and a common energy management system for this setup, so that all the assets are generally owned by the single company. So they have full control and visibility of all the resources. And we are focusing more upon the energy management system in this presentation. So what it is doing is taking the weather forecasts and weather data into considerations for solar and wind power, and also considering the electricity markets or the hydrogen markets where these commodities are being sold to earn the revenues. And this is how this hybrid power plant is being designed and being considered. So the motivation behind studying this kind of co-located configuration is that we can accommodate more RES with the same grid connections, and there is an optimal utilization of the land with this, and even the reduced curtailment because we have uh, like anti-correlated two renewable resources connected at the same point. So when wind is not available, maybe solar is there, so we can inject the power into the grid and vice versa. And on the top of that, if we have excess of wind and solar both, we can also utilize the electrolyzer to produce hydrogen and increase the revenue for the hybrid power plant owner. So with all these motivations, this kind of configuration is being studied, and how we are modeling it is using the tool called HyDesign, which is a Python-based open source tool. And it's a software platform for the design and operation of such utility scale hybrid power plants. And in this tool, we are capable of doing wind turbine, wind plant siting and layout optimization, PV array siting, energy management system optimizations, including battery, hydrogen, degradations of different components. So all these things can be done together. And since all these individual problems are in different backgrounds and different having different characteristics, and they cannot be modeled in the same frame in the same way. So that's why we have used OpenMDAO platform, where this can be modeled as a coupled optimization, and each component can be linked with the another component for which is for completely different purpose, and we can use the input of one component as an output for the output of one component as an input for the another component. I'll show you that thing in the next slide. How is this implemented? But that is just for the background, like how the whole design and operations of such multi-technology hybrid power plants are being modeled in the tool. And coming to the utilization or the purpose of the tool is that we can do both operations. Like if we are having an hybrid power plant and we want to evaluate the design is given for us the capacity of different components, then it can be evaluated, like what will be the net present value, what will be the cash flow or revenue for this over the lifetime of the plant. So that design can be evaluated. Or even if we don't know the design, and if we know the location of the plant and the available grid connection capacity, then we can size the whole hybrid power plants, like what all combinations of technologies makes more sense at that particular location. And the objective function which we can choose here is that either we can minimize the levelized cost of energy or we can maximize the NPV over capex. So NPV over capex is a indicator of the profitability of the plant, where the net present value is increased with respect normalized to the capital investment. And as I just explained in the previous figure, that the key components that we are considering are wind, solar, battery, hydrogen, grid connection, and also we can design a plant which is off grid, which is islanded with zero grid connection, and maybe having a Power-to-X facility so that we have some off taker for the electricity produced. And this is the link link to the web page where we can further explore HyDesign, and there are few tutorials which anyone can run even in the Google Colab, just to get familiar with the tool, how it works, and try running some hands-on exercises, and all the instructions on how to install HyDesign or how to run some simple designs with some given example sites are being given on this web page. So you all are welcome to explore it further. And then coming to the workflow of this tool. So the left side figure is basically the detailed version, how the data is being flowing within the tool. But to begin with, I can quickly explain that from the right hand side small figure. So basically, we are collecting the weather data for the given location first, that is the emphasis, and then once we have the wind speed and the solar irradiance for that location, then the next component, which are the wind power plant design modules and power PV plant design modules, they will convert those weather data into the equivalent power output profiles. And then we have the energy management system, which uses the available wind and solar power and then decide the operation of these components, like when to charge the battery, when to discharge the battery, or how to participate in the given electricity market or the hydrogen market. And then once we have the operational time series, then the finance block calculates the different financial components like NPV, LCOE, IRR, all those KPIs. And then on the top of that, we have an outer loop where the sizing optimization is being taking place. So if we further want to size a plant, then we can choose one of the objective function, and those design variables will be fed back to the upper upper blocks having the flow of whole data. So this particular block on the right hand side is further expanded and being shown on the right hand side big figure XGSM diagram. So which gives a glimpse of like how what all inputs are coming from the different components, and how those outputs are being used further by the other components, like when we are calculating the cost models, or when we are doing the calculating the financial KPIs. So this is how the data flows, and then we feed back again the design parameters of the plant to size the plant for that given location. So it might be a bit tricky, but the given reference here gives a complete detail of this tool and how it is being evaluated. Then in brief, just to summarize how what as a user we need to do the optimal sizing of such hybrid power plant. So we can consider the tool as a black box where we are doing the optimization or evaluation, and as an input, what we need to give is the electricity prices. For example, the spot market electricity prices, if we are considering that revenue, we need to know the hydrogen prices and what is the demand of hydrogen. Then the site location, so that we can extract the weather data, and the technologies cost. So if we are having multiple technologies, so we need to provide the technologies cost as an input. Is someone saying something, because I can hear some voice? Okay, I'll continue then. Once in this whole black box, when we are giving these inputs, what we get as an output are the design variables, like different design characteristics of the wind turbine. For example, its rated power, how many number of wind turbines we need, what will be the rotor diameter, hub height. Similarly, for solar plants, we get to know what will be the tilt, what is the optimal tilt angle, azimuth angle, or AC power capacity. Similarly, for batteries and electrolyzer, we can get all the design specifications that we have provided to the tool. And also as an output, we get the financial KPI values as well, which includes how much is the annual energy produced or how much is the annual hydrogen produced, what is the total curtailment, internal rate of return, levelized cost of electricity, levelized cost of hydrogen, and all those things. Then coming to the input details, so as I mentioned, like technology costs and parameters. So for those people who are from industry, it is quite important for them to understand like what all kind of costs we are considering. So here I have tried to put one slide with some breakdown and assumptions of cost that we are considering. For different technologies in the tool. So for example, for wind and solar, we are considering the equipment cost and the installation cost as a capex, and then operational and maintenance cost in opex. And of course, we can also enter their degradation rate because we are designing a plant considering its operation for the whole lifetime for around 25 years. And then for the battery, again, we are considering the energy and power cost, the characteristics such as efficiency, depth of discharge, level of health, and everything, so that we can also find out when a battery needs to be replaced and how many number of battery replacements are required over the whole lifetime. And additionally, we need to provide what is the grid connection cost. So because this is an important aspect, because there is a lot of electrical infrastructure which is required for connecting a plant to the grid. So that grid connection cost also matters a lot. And this cost definitely increases a lot if the plant is offshore in comparison to the onshore configuration. And then we have to also provide balance of system cost and discount rates, tax rate, inflation rates, etc. for doing the financial evaluations. And then coming just giving an overview of how EMS is modeled for such plants, because in the EMS, we are trying to find out what is the optimal operational strategy for a plant, when it should give power to the grid or when it should supply power to the electrolyzer to produce hydrogen. Because there are some instances when we have a low electricity price period, then at that time it is good to produce hydrogen. And if it is like a high price time interval, then it's good to discharge the battery also and to supply power to the grid. So those kind of decisions are being taken within this EMS, provided that we have given the electricity prices and the hydrogen prices as an input to the whole setup. And on this basis, we have done some case studies for some locations in France, Germany, and Denmark. And we are doing the evaluation of a given design. So for example, we have a plant of 360 megawatt and wind and 80 megawatt solar, and the grid capacity is around 300 megawatt. And hydrogen price is €5 and electrolyzer is PEM with 80 megawatt. So with this, what we have observed is that, of course, in the first graph, we can see the total curtailment has reduced significantly with power to hydrogen setup, because whatever power is being curtailed earlier due to the limited grid connection is now being used to produce hydrogen and earn more revenues. And that has added on to the NPV over capex, which is the profitability of the plant. And at the same time, the grid utilization factor, which is basically the measure of how much we are utilizing the grid, available grid capacity, has come down with power to H, because now all the time sometimes we are not supplying power to the grid, rather we are producing hydrogen. So in that case, this is an indication that if we have a power to hydrogen setup, then it could be beneficial if we also optimize the grid connection capacity requirement. So in such cases, instead of asking for like 300 megawatt of permit, we can also end up just with 100 megawatt of capacity, and then using a more hydrogen production in that scenario, if that is profitable. So this is one thing, which is the evaluation of a given hybrid power plant design, which can be done by HyDesign. And the second thing, which is the sizing optimization, which we can also do with HyDesign, is being done with the same setup. and giving the location of the plant and all the inputs as I mentioned earlier. So with this, so here along with the EMS, we are also continuously updating the design parameters of the plant so that we know where when the solution converges, then we know what is the optimal size. So here I have presented few results for sizing optimization with different hydrogen prices just to show that how the size of electrolyzer is impacted with the change in hydrogen prices. So we can see that when the hydrogen price is very low, that is 3 euros per kg, then just a very small electrolyzer of 1 megawatt was enough, because and it was preferred that let's get the power curtailed, because instead of investing in electrolyzer and earning some amount of revenue won't be a good business case because hydrogen price is quite low. That's why we are maximizing NPV over capex, because with every technology and investment, the capital investment also comes up. So it's not only about just earning the revenues, but we are also investing. We are also having the investment cost. So it's good that we are considering that as well. But when this price increased to 5 euros per kg, the electrolyzer capacity is also increased. It increased to 132 megawatt. And we can see that there is no curtailment here in this case. And when the hydrogen price is 8 euros per kg, the profitability has increased multifold, and P2G has also reached to 200 megawatt of capacity. But in this case, again, the grid utilization factor, which is GUF, has reduced a lot. So if we have a very high hydrogen price, which might not be the case in future, it's good even if we ask for a less grid connection. So this is how the sizing optimization takes place for a given scenario and given inputs. It can let you know what could be the optimal configuration. So it might happen that a site is not at all good for hydrogen production, or it is not good for wind plus solar and only wind. So all these kind of analysis can be done in this tool. And then there is one more case study that we have done with offshore case as well, and for grid connected and off-grid hybrid power plant both. So what we have tried to do is we have tried to change the electrolyzer capacity and the grid connection capacity for all these three locations. And what we have observed is that for Denmark offshore, for example, the last one, it is preferred that we don't have any grid connection, rather going for a very large size electrolyzer. Because as I said, the grid connection cost with the offshore configurations are pretty high. So it's fine, like if we live up with the islanded hybrid power plant just producing hydrogen. While in France onshore, higher grid connection is preferred with a 200 megawatt of capacity and a small electrolyzer, probably because the electricity prices in France are higher, so it is more profitable to earn revenues from the electricity market than producing hydrogen. While in Denmark, onshore grid capacity was 150 only, and electrolyzer was a bigger one than the France onshore. So these kind of studies all can be modeled in HyDesign, and we can find out at what location which configuration makes more sense. And then, as I said, this is the last part of my presentation. So as I just mentioned that we can all produce hydrogen, but on the top of that, we can also produce ammonia and other energy vectors which are derived from hydrogen. And we can sell that commodity directly into the market. So here we have also modeled the ammonia production and ammonia market in our work. So with the research questions that how we can maximize the value of renewables when producing green ammonia, or and in this work we have also done the detailed analysis of what different electrolyzer plays a role, because we have different types of electrolyzers, alkaline, PEM, SOEC, and each technology has pros and cons. So how does it impact the ammonia production and the overall profitability of the plant owner? And with the given setup, how much additional revenue we can accommodate, how much additional renewables we can accommodate behind a single point of behind a given point of grid connection, and with this can we reduce the dependency on the grid.
I should come and do that.
And then again, just adding on to what I have shown earlier, like if we are producing ammonia in this case, we have three market options. Like there can be hydrogen market, ammonia market, and electricity market all. And now the EMS will decide on in which market it is profitable to sell the energy. It might be possible that in some instances it is not profitable to produce ammonia and just using the hydrogen market. So all this analysis we have also done, but this work is not yet published, so I could not put some results here. But just to give an overview of how we are modeling power to ammonia in HyDesign, I have just tried to put one slide over here. And also ammonia and hydrogen prices, we are considering them as constant, and regarding their demand, we can consider them as like infinite demand, like whatever we are producing, we are selling, or even a user can provide a given demand profile of any industry, and then the EMS will try to meet that demand as closely as possible, and then the revenues are calculated accordingly. And I think that's it from my